Hello everyone, welcome back. This is Gautam Raj Mokhtan
This is Sandeep Tamrakar.
And this is Prajwal Osti.
for Table TechTalk, where we discuss things that we find interesting in the world of tech. Today, what are we going to talk about?
We could talk about it, just about anything.
All right. What did you find interesting? Was there anything about?
Yeah, so there was this talk about some legislation that was talking about they are trying to ban this encryption in the EU because somehow people are trying to communicate and then the government cannot intercept it anymore.
Oh,
So there are these talks of banning in encryption, and then I thought,
encryption in general,
yeah,
or
yeah, in these applications like in your WhatsApp and everything, so they have this end-to-end encryption now, and then because it cannot be broken technically, as it used to be, probably used to be, so now they want to like do it legally.
not by technology but
Yeah,
by process?
By process, you
Okay.
you are not allowed to encrypt certain things when you are communicating or I mean you should
But
share.
I guess
the keys with the government.
once there is a quantum computing, this problem will be solved for the
Yeah, they don't
government.
have to. Yeah,
Yeah,
again,
they
can
don't have to worry
break
about
it
that one.
again.
Yeah. So you can have some technical solutions coming.
So maybe we could talk about like quantum cryptography or post-quantum cryptography.
Yeah, and that's interesting topic.
So today, what we have is end-to-end encrypted communication. Let's say we do a WhatsApp call. It's end-to-end encrypted, and what that means is that nobody, even if they intercept the whole, in the middle, and then they get all the data packets, they cannot decrypt what was said between the two people at the ends, because it's encrypted fully on the path.
I believe so because I mean for Facebook I think the business model is that they're able to read your messages and then accordingly serve advertisement or sell or use your data. I mean it doesn't make sense for them to not to be able to read them. If they are storing, then it doesn't make sense if they don't.
Yeah.
Decrypted.
Okay. So regardless of that, the point is that let's say the Facebook as a company is saying that, hey, we have the capability because it's in our terms of service that we can do whatever with your data. They are just all clear from that. But let's say the government says like, okay, we want to intercept outside of Facebook's purview. They want to intercept and decrypt it. Then with today's encryption technology, it's really difficult or almost impossible for any third party to crack what was the key used to encrypt that piece of data. And with quantum technology, what you're saying is that it will be possible to be able to guess or to come up with the key that was used to encrypt.
So most of the cryptographic algorithm today is based on public cryptography is based on a factorization problem, a logarithmic problem, and elliptical logarithm problem. So if you take a RSA encryption, for example, they use this factorization problem. Like you take two large prime and multiply them. Given the product, you cannot get factor the prime factors in polynomial time. But if you have those numbers, it's easier to multiply. But then it's really difficult to get its prime factors given just the product. So this is a hard problem. And most of the cryptographic algorithms are based on, especially this RSA, is based on this factor. But what quantum computing promises is like this SOAR algorithm that finds these prime numbers in polynomial time. Mm-hmm. So if it currently takes like 2,000 years, then maybe it can break these or find these prime factors within maybe 8 minutes or even shorter time. So in polynomial time. So then
So that's the promise of quantum computing.
that's the promise of an algorithm that that's
So
being used.
if quantum computing is today available, to the extent like quantum computing is still in a POC stage, right? Like only there are
few sort of things.
Yeah. So you need to have those cores, let's say quantum cores. So what is that equivalent? Things that you need to have them in enough amount to make it
Qubits, you mean?
Qubits,
Quantum bits.
Yeah, quantum bits. You need to have them in enough amount, which is not there yet, but eventually it will be. And then given that, the Shor's algorithm promises that you will be able to come up and generate those factors easily and in realistic time. That makes it worthwhile to use that technology to start breaking these encryptions. But today it's not there.
Well, there are things like I've read like RSA encryption with 2K keys, like 2048-bit keys. They can break it within 9 minutes. Something.
With this massive GPU.
You mean from using today's technology or using this
Quantum technology that's being used today.
Okay.
So then, so there's that wave coming.
Before that, I have to clarify that it says that they were able to break this 2048-bit RSA key within 8 hours, given that there are 20 million qubits
available in that pool. Yes,
yeah,
exactly.
So
Today's technology that is producing these quantum labs in the chips, we don't have that in the thousands yet. But maybe in 2030s we will reach that point. But coming even before that, let's say just coming about password cracking and this whole thing. So we had this this whole thing about easy passwords, like brute force cracking, right?
Yes.
Just guessing a repetition and then hammering it through. So that was used to easily guess this MD5 numbers or some dictionary attacks and those things like that. But what we are talking right now with this is a space that is way more complex, and you can have a lot more difficult passwords in place that can easily be decrypted if they are using the algorithm that powered this PKI.
Yeah, sort of like this qubits is amazing. When you talk about bits, it's either 0 or 1. But qubit, it can be both 0 and 1 at the same time. They are the value of the bits is superimposed 0 and 1. Like, let's first think about like how can it be possible. It's very difficult to imagine the situation like both 0 and 1.
The quantum states, you mean?
Are the quantum states.
But before that, I just wanted to establish like the space that we are talking here is not our regular Tom and Jerry's regular passwords that we are trying to crack here. We are talking about this specific way of communication where these asymmetric keys are used, right?
So even this asymmetric keys, you're saying this based on this prime factorial problem.
Yeah.
So if you solve this factorial problem in polynomial time, then you crack the algorithm, right?
So that's the kind of the background on which this argument about encryption, decryption is happening, is that one party definitely knows the key, but the premise is that anybody else who does not have that key should not be able to crack it. But quantum computing is going to be able to crack it, and what are we going to do in that state of the world is the question, right?
Yeah. So NIST, the National Institute of Science and Technology, they have started this post-quantum cryptographic competition or sort of preparing this encryption signature algorithm for when quantum computers are prevalent.
So we need to come up with different kinds of algorithms that allow for this asymmetric what is it called? Asymmetric cryptographic exchange.
Yeah, so most of this symmetric key cryptographic like AES and all, they are sort of quantum safe because like if you tweak some stuff, like if you increase the key length, then it might be even difficult for quantum computers to break the symmetric key. So what they are looking after is basically signature schemes, which is quite essential to prove your identity, for example. And then public key cryptography, like asymmetric key encryption. But mostly this asymmetric key encryption has two phases. One is to provide this digital signature, and another is used to encrypt the key, encrypt the key. And this key is actually used to encrypt the data. So data is encrypted using symmetric key, and this symmetric key is again encrypted using public key.
So is it? So now how things work is that somehow if they can access your public key, then they can easily find your private key with this quantum computer. Is that so now? With this quantum computer, this public key can give you.
Public key may be able to provide some sort of help clues. Yeah.
Because isn't this public key now this product of these big prime numbers? So it is by nature it's public, so you can access it, and then
but
you
the
just
challenge is to guess the exact factors
Yeah.
that of that number.
Yes.
And that is the private key part.
Yeah.
Yeah.
So
And guessing that private key, somebody figured out that okay, if we have quantum computers in place, we can exploit some property of the quantum states to guess which factorial was used for that prime.
It allows you to do this testing pretty fast.
Yeah.
And since like qubits, they can be in both 0 and 1 at the same time. So if you represent, for example, three bits, then it's all zeros and all ones and in between them. So its value can range from 0 to 7 all
at the same time.
At the same time.
Exactly.
And then they have in quantum computing they have some sort of operator which filters out wrong answers and with some probability, high probability, will output the answer. So that's one way of doing brute force pretty fast.
I saw this one nice simulation about this how to filter out or how to start filtering out the right guesses, because there was some Fourier because there is some periodicity involved that you can use to apply some Fourier transforms and get to the exact number that corresponds to this calculating the R value of this. There was this weird equation used to solve prime numbers.
Yeah, so source algorithm. Source algorithm. You mean.
Source algorithm. Yeah.
Yeah. In what I've understood is you pick some random guess, and then you multiply this number with its many times with the same number, and then you somehow find the product of the.
So the equation was g to the power of r plus 1 equals to n or something like that, and then to calculate the r, you get this, and then
you
somewhere
can do
there,
this sort of a multiplying quite easy, fast, and then do some checking. But so this quantum computing will definitely reduce this efficiency of this RSA or most of the public key cryptography used today. So this NIST, coming back to NIST again, they have started from I think from 2017. They have started this competition or standardization process where they had 69 different algorithms which were entered in this competition, and most of this quantum proof or quantum proof cryptographic algorithm falls into 6 different categories. The first one is this lattice-based encryption and signature schemes. Some of these schemes are only useful for encryption, and others are only for signing. So some of them are like useful for both this purpose, like this lattice-based, which can be used for encryption and signature. So they use this lattice as a cryptographic primitives. And then there's like a multivariate quadratic signature, which uses this multivariate polynomial things. And then there are like hash-based signature, which uses hashing technology, and then code-based encryption, which uses this error-correcting codes to encrypt. Then there are like a super singular elliptical curve isogenic cryptography, and then for symmetric key, they use this quantum resistance techniques like using large size of keys and so on. But mostly they are using the earlier four algorithm based on this lattice-based, multivariate, hash-based, and code-based were there in the in the competition, and I think they are in fourth round now. So there should be, NIST already has published some of the winners already, like this Crystal, some Kuiper or something, and then that's one of them. But I guess next year, somewhere next year, probably towards the end of next year, they will, by 2024, they will have a list of winners.
Okay, list of
announced.
Was it like they provide this list of approved algorithms that are okay to be quantum safe for secure communications?
So how are they judging these algorithms?
They invite lots of these academics and,
okay.
and other
peer review
reviews. They do this review and also put in some sort of how you can break this cryptographic algorithms.
So
there are lots of academic.
So do you think the world is safe for when the quantum computers are here to be safe from
I guess
these
we have
dangers?
been starting earlier at this point, and quantum computing is nowhere near looking from today. At least there's some sort of a breakthrough. But like
but there are always these legacy systems that are still using
old
they're
still using this how do you call it, triple DES and DES.
Or no encryption.
Or no encryption, plain HTTP or this kind of old systems that are hard to maintain or improve. You can't even, there's no upgrade path for many of these legacy systems.
Like especially if it is implemented in the hardware itself, and then it's quite costly to replace all these hardware. But nowadays it's more easier. We have this over-the-air firmware updates. And thinking about quantum computing, it's not only like I mean, we are only talking about like today's cryptographic algorithms can be broken easily, but quantum computing also provides this quantum cryptography, a branch of cryptographic algorithm, which provides you sort of solves today's problem, like key distribution, for example. So the quantum has this quantum key distribution mechanism. They use, like if you think about quantum computing, it's quantum computing computes by exploiting the properties of physics and not the maths. So what they use for quantum key distribution is like photons. So they, how do you call it? They polarize photons, photons, and then the photons could be represented in horizontal or vertical form or some other different angles. And then you transmit this photons from the sender to the receiver. So I want to distribute I want to establish a shared key between you and me, then I start transmitting these photons. So these photons cannot be copied like digital data. So if somebody, like if Prajwal is in the middle listening to or intercepting these photons, then you will not get the correct polarized form of the photon. So we end up in different patterns because it cannot be copied. So if he has to intercept, he receives these photons itself. So you will not be getting this polarized photon.
So you mean that we lose this replicability of this digital technology? I mean, one problem now is that you can exactly replicate what the other person has, and then,
but nobody knows. Like
So
Yeah.
is this then like communication is happening through optical fibers that the photon
this
is passed
is
through
just
that,
a,
or is it like a-
concept,
It's just
conceptual,
okay.
or they have been developing in some labs. But think about the idea. This is the data that is not being able to copy it. So if somebody intercepts, you know that it has been intercepted. So this way they are thinking about like quantum computing to solve key distribution problems and all.
yeah, I think I mean this replicability of these bits is like a good thing that enables so much to us, do so many things. But then the downside is that it is replicable, and then the secrecy may be lost. So I had never thought it like that before. Like,
Yeah, picturing this is a bit different. I remember we used to have this in this whole illustration of this communication with this Alice, Bob, and the Eva and the Eve. Yeah, so there's actors that are participants in this communications happening, and where then the Eve is the one who will someday possess quantum computing capability, and that's the day for which NIST is preparing these new standards to protect against Eve, right?
or they want to be the Eve
So
themselves. They want to get ahead in the game.
So let's hope that quantum computing arrives quite soon.
But the other use cases of quantum computing are not that prevalently, or
I
like
think,
people are not
for example,
thinking.
for maps and navigation, it's like you can look into a multiple path from place A to place B, and then analyze at the same time, because quantum computing can take more than one data at the same time.
You mean
and
like
then-
parallel
then-
computing?
Yeah, I
then
think-
it can determine which one is the optimal solution. So I think it's more useful.
But the problem has to be designed in a way that fits the quantum computing paradigm. The computing paradigm is different. So for the way you have developed this Schur's algorithm cracking using the Fourier transform across these excited states. So that way, so all problems, if you want to solve it through the instruction sets will have to be somehow defined. Maybe there will be some sort of compilers or binaries that will do all that stuff for you. But yeah, today it's kind of only a select group of problems are the candidates that can benefit truly from quantum computing.
Yeah. Only certain problems have these solutions in quantum. So there are these hard problems in computing that even this quantum cannot easily solve.
Yeah, that's how this post-quantum
Yeah.
cryptography are based on. Like.
They should be based on that, because it's only one class of problem that it makes easier to solve, the way I understand it. And then there are still like other problems that are hard still. So we need post-quantum computers to solve them or crack them maybe.
So in a way, yeah, we are quantum safe. And no need to worry, no need to already share your stocks in tech companies.
Next year we will be having some sort of approved algorithms for post-quantum cryptography.
Yeah.
And let's see how fast the industry is going to adopt them.
Yeah, good. That's pretty much quantum computing. What I knew. Thank you, Sandeep Dai, for enlightening me with more information on that front. All right, that's it for quantum computing. Bye bye.
See you in the next video.